Hey there, lie low. It's an earthquake. Thank God, that was not a strong earthquake. By the way, do you know how to determine the intensity of an earthquake? Yes, by using a Richter scale. Did you know to study and find the range of magnitudes of earthquakes, seismologists use derivatives? Let's learn more about derivatives in this video. We are familiar with the term velocity, which is nothing but the rate of change of displacement. In case the object is moving too fast, then we need to know its velocity at every stage. That is, its instantaneous velocity for making the required changes. This is possible only if we are aware of the concept of derivatives. To understand the concept of derivatives, let us proceed from what we have already learned. We have learned that the slope of a line is constant throughout and is given by slope is equal to rise over run is equal to change in y-coordinate over change in x-coordinate. It may be noted that the slope is the same regardless of which 2 points are used to compute it. It means slope is constant for a straight line. Now let us understand the idea of the slope of a curve. Slope of a curve. The slope of a curve at a point is nothing but the slope of tangent to the curve at that point. We observe that the slope of the tangent to the curve is not constant. It keeps changing at every point along the curve. Thus, the expression slope of a curve is meaningless, and we have to be specific by stating it as the slope of a curve at a point. Once again, this is possible by finding the derivative. The derivative of a function gives us the slope of tangent to the curve at any point on the curve. Now we proceed to understand the geometric interpretation of derivatives. Geometric interpretation. We consider the curve given by y is equal to f of x. Each point on this curve will be given by the ordered pair x f of x. Let p x f of x be any point on the curve. We consider another point q very close to p on the curve. Let the x-coordinate of point q be x plus delta x, so the y-coordinate of q will be f of x plus delta x. The slope of the secant line PQ is equal to rise over run is equal to change in y-coordinate over change in x-coordinate is equal to f of x plus delta x minus f of x over x plus delta x minus x is equal to f of x plus delta x minus f of x over delta x. We observe that as we keep decreasing delta x, point Q keeps getting closer and closer to point P. And when delta x is sufficiently close to 0, secant line PQ becomes tangent to the curve at point P. So the slope of the tangent at point P is equal to limit delta x tends to 0 f of x plus delta x minus f of x over delta x, if the limit exists. This expression gives the slope of the tangent to the curve at x f of x or xy. This is the derivative of the function y is equal to f of x and is expressed as f prime y prime dy over dx or d dx of f of x. Thus the derivative d dx of f of x is equal to dy over dx is equal to limit delta x tends to 0 f of x plus delta x minus f of x over delta x. We observe that the derivative is the instantaneous rate of change of the dependent variable with respect to the independent variable. The process of finding the derivative is called differentiation. Illustration. Find the derivative of the function f of x is equal to x squared. using the expression f prime of x is equal to limit delta x tends to 0 f of x plus delta x minus f of x over delta x, we have f prime of x is equal to limit delta x tends to 0 x plus delta x the whole squared minus x squared over delta x is equal to limit delta x tends to 0 x squared plus 2x delta x plus delta x squared minus x squared over delta x is equal to limit delta x tends to 0 2x delta x